Alrighty, so let's see, what chapter are we on? Oh, yeah. Okay, so hi, good morning. This is gonna be today is gonna be our last day in chapter 4. We may start on chapter 5 today, depending on how quickly we're going through this stuff. Um, Otherwise, we will be starting chapter 5 tomorrow. So, yes, exciting stuff. So, we're going to be talking today about doing math now with some of these things in solution. So, you guys have been terrorized quite a bit about how reactions are happening, double displacement and single displacement reactions. And we also spent some time talking about oxidizing agents, reducing agents, that sort of fun stuff. So here we're going to be now applying our stoichiometry to reactions that happen in solution. So previously, we kind of had this idea that we could go from grams of substance A, oh my goodness, 2 moles of A, 2 moles of B, 2 grams of B. Right, we had this before. This was kind of our stoichiometry. And we could use conversion factors, right? We were using molar masses in the case of grams, right? And then we used our almighty reaction coefficients to do that middle part. What we're going to do today is, so these grams that we see here on this list, those have to be pure substances. All right, so like if we were taking our hydrogen gas and reacting it with oxygen gas, those were 2 pure substances, right? They're two compounds, or 2 elements rather. And so we take those 2 elements and we react them together, and poof, we have now made water. And water being a pure substance as well, that one's a compound. We can figure out its mass by knowing the mass of hydrogen and oxygen that we put in. So those are typically just going to be solids, liquids, or gases. However, for solutions, which are mixtures, we have a different way. We can't use grams. I don't want to say we can't. I'll just say we use concentration instead. Wow, that's really ugly. Okay, let me try that again. Concentration. So note that concentration is basically a way of saying how much of whatever we're looking at is dissolved in our solvent, which is typically going to be water. Did we talk about solute, solvent? Well, hopefully those are familiar terms anyway, but solute is the thing that's being dissolved, and the solvent is the thing that dissolves it. So for us, water will be our solvent pretty much all the time, and the solute will be, various salts or acids or whatever ionic compounds we're dealing with that are being dissolved. Those are solutes. Okay, and we have a couple ways of talking about it. The most common one is called the molarity, which is given as a capital M, and that is going to be moles of solute. Again, that's the thing that's being dissolved. That's going to be the compounds that we're looking at over the liters of solution. And so we can calculate the molarity of something by understanding what that means. Let me just write a question here. Oops. Alrighty, so if I gave you a question like this that said 25 grams of sodium chloride is dissolved in water to make 500 milliliters of solution, we can calculate its molarity. What we need to understand here is that this is just units that we need to work with. As always, we're never, ever, ever going to forget our unit conversions, right? So we need to get this 25 grams, we need to get that into moles. And we need to get that in milliliters into liters. Okay, so how we remember going from grams to moles. The unit or the conversion factor we use there is molar mass, right? So we would calculate it, what is it, 58.44 grams per mole? I think that's the sodium chloride. And to go from milliliters to liters, we have to remember that we have that's 10 to the minus 3 liters, right? Just metric prefix stuff. So, if we wanted to calculate the molarity of the solution, 25 grams times our molar, 1 over our molar mass. Let's see here. Let's bust out that calculator. 25, 58.44. Kevin, I'm sure, has already put the answer for me, but let's just see. So that is 0.427789, let's say, moles. Okay, remember we're going to want to keep track that we have 3 sig figs here. For 500 mLs, 2 liters, we can do that. That's half a liter. All right. Hopefully none of this stuff is confusing. So understanding that molarity is moles per liter, we can now plug those guys in. And we get 0.85. Let's do the sig figs for us. 856. Okay. You can either leave the units as capital M, which is read as molar, or it's the same thing as saying moles per liter. Okay, so these are, both of these are equivalent. So you can say molar. This solution is 0.856 molar. It has a molarity of 0.856, or it is 0.856 moles per liter. Any of those, it's all the same. Okay, so this is how we're going to talk about concentration. And as we can see here, whoop-de-doo, molarity is a conversion factor between moles and volume of solution. That is what we are going to see here. It is a conversion factor. We love conversion factors. All we ever do in chemistry is unit conversion, it seems. So this is now an additional conversion factor we're going to have. So, that being said, we can add on to our handy-dandy little chart here. We remember the only time we can ever convert between two substances is if we have a chemical reaction and we're going to use reaction coefficients, right? So, we know that we could go from the mass of substance A to moles, but now we have an additional one. We can now go from volume to moles if it's a solution. And guess what? We can do the same thing with B. I don't know why I put a period after B. Erase it. So remember, this is the molar mass up here. And now these are molarity. Let me just erase those arrows. I don't know why I put them. And as always, the almighty reaction coefficients. So, we now have two more little things we can do to mess with our math when it comes to reactions. So let's go ahead and do an example. So I'll just leave this up for a second. Basically, when it comes to this, we're going to see that we are going to keep adding onto this chart. We're going to have one more thing to add on to it later on. But the same thing is going to happen here. So we're going to be starting with 1 unit of whatever substance we have. That'll be A, right? Whatever that happens to be. We'll have a chemical reaction of some sort that'll give us coefficients. And from that, we're going to be able to take whatever quantity of A we have and convert it into whatever quantity of B that we're looking for. And so using a little chart like this is going to kind of guide us in how we're going to do that. So here's a question. If I had, or let's see, how let's see, is required to react with 162 milliliters, here let's just say of 0.750 molar NaCl solution. So, this is how a question might read that's going to deal with these sorts of concepts. So, I'm asking you how much of a volume of a solution that we're going to have. That solution, I've given us the concentration, and we are going to react that solution with a particular volume of 0.75 molar sodium chloride solution. Not sodium chloride, that's not going to react. There we go. Sorry, sodium sulfate. Let's do that instead. I apologize, that would have led to no reaction. That wouldn't be fun. So, lots of things to look at in this problem. We have a lot of numbers. We have a lot of words. I think a good idea might be to kind of pick out the quantities that are in this problem and then the substances as well. So looking at this problem, we have two substances, right? We have barium chloride and sodium sulfate. Well, hopefully that's not crazy. You can see those two are the substances we're looking for. And we know that we have... Is there any way I can salvage this? No. Our solution for barium chloride is given to us with a molarity of 0.25. And we know we're asking... The question is asking how many mLs of that solution we need. And the sodium sulfate, we know our solution is 0.75 molar, and we have 162 ml of that solution. Okay, so I've kind of just grouped up the numbers that we have along with their units with our substances. And from this, we're going to see that we can work with these. However, first things first, we're going to need to write a chemical reaction. Ooh, how exciting. So, let's do it. So notice all of this stuff, which I'm sure you already hate, is just going to keep building upon our knowledge of what's happened before. So we have a reaction, but we don't have products. However, you guys know how to do this, right? What type of reaction is this? It's a double displacement reaction, right? And so that means things are going to swap partners. And so the products of this are going to be sodium chloride and barium sulfate. Note our states of matter. It's told in the problem to us that these are both solutions, so those would be aqueous. And we know that sodium chloride would be aqueous, but barium sulfate would be solid, right? This is a precipitation type reaction that you guys have done 1,000 problems on, so hopefully that's becoming more and more second nature. And then throw in the 2 for balancing, of course. So, in this case, we're looking at barium chloride and sodium sulfate. So, we always want to start with the one that we have the most information about. So, we always want to look at the quantities we have and evaluate, can we get moles somehow from the information that we're given about these substances. About barium chloride, we cannot get moles for that directly. All we have is a molarity, which does not tell us moles directly. However, if we look at the sodium sulfate, we have molarity, which remember is a conversion between volume and moles. It's a conversion factor there. And we have a volume. And so therefore, we can figure out what the moles are. That's to balance the equation, Gerson. Right? We have 2 sodiums on the left, 2 chlorines on the left, so we need to put a 2 on the right side. Just to balance it. Yep, no worries. So, but we're going to see right now we didn't even need that. So, let's start. Essentially what this reaction is telling us is we are converting in between. Let me switch to a different color. We can plan this out. We are going in between sodium sulfate and barium chloride. That is one conversion we're going to do. So, we remember the only thing we can change between substances is moles. We have to have moles to go in between 2 different substances. We know the question is asking us for volume of barium chloride solution. And the problem is giving us a volume of Na2SO4. Yeah, so we're going to be doing just some conversions, just like before. So, just this is our plan for our unit conversion. Remember here, now this is where molarity are going to be our conversion factors. And in the middle, as always, are our reaction coefficients. And since when we're dealing with molarity, our volumes need to be in liters, we could go ahead and convert that. So, I'll just do that here. You're going to be doing a lot of milliliters to liters, so hopefully this is not anything too crazy. I'm just going to do that in my head. You guys should probably at this point be able to do that in your head as well. It's just times 10 to the minus 3, so that's all we have to do there. So, let's go ahead and go through it. So, we have 0.162 liters of sodium sulfate. We see that's what we're starting with. That's our volume. We see that in our plan, we have our molarity to go between moles and liters. And the problem tells us that's going to be 0.75. That's the molarity of the solution that we have. And now, so that's the molarity we've put in. So now we are in moles of sodium sulfate. So we're going to use our reaction coefficients, which were both 1. As you see, we have balanced the equation. Same coefficient there. So we have put that in. And now we are going to go ahead and use our molarity to figure out what the volume of barium chloride is going to be. And so the molarity was 0.25. Remember, molarity is converting between moles and liters, so it's always going to be 1 liter, and you're going to have your moles, and Kevin has already done it for us, to be 0.486 liters, which is going to be equal to 486 milliliters. Since I did technically ask for milliliters in the question, you will need to convert that, but that's it. And that's going to be of this solution. Okay, so does that make sense? So when you're dealing with solution stoichiometry, it's the same sort of idea. You're taking whatever unit you're given, using conversion factors to get it to moles. You use your reaction coefficients once you're in moles, and then whatever you need to do to get it into the unit that you're asked for of the second substance. Is that so? Any questions on that? While you come up with questions, if you have any. This question had a secret part B. 10 to the negative 6. I think it should be 10 to the positive 2. Double check, Star-Lord. Just to be sure. While you're double checking, I will write question part B. So question part A was asking us how much barium chloride solution we needed to react. In this case, Sienna, because I said in mLs in the question, we're going to want to do mLs. So it's just whatever is being asked for. So if I asked for liters, you would leave it as 0.486. But in this case, I asked for milliliters. Alrighty. So this time we're looking for how much barium sulfate would be produced in grams. So slightly different, but again, should not be new. Remember, we can go from moles of sodium sulfate to moles of barium sulfate. Right? That's part of our reaction. So, since this question is asking for grams, that'll be the end unit that we have. And so for our plan again, we remember that we'll have the volume of Na2SO4. So this is the plan. So again, we always start with that middle part. That's our reaction coefficients. So remember, that's the only way you can go between moles of a different substance. And so, that's our coefficients. And so we know we can go from volume to moles by using the molarity. And now we can remember, okay, how do we go from moles to grams? Oh, that's right, it's molar mass. So all stoichiometry comes down to is planning your route and identifying the conversion factors that you're going to need to get there. So we have planned out, starting from that middle part using the reaction coefficients. We know we're asked for grams of barium sulfate, so that'll be where we're going to end up. And we know we are given a volume to start with. Yes, very good point, Gerson. If you wanted, you could use barium chloride instead. It does not matter. So you could have planned a different way. You absolutely could have. And we're going to see that it's the same idea. molar mass here, and then the coefficients. Yes, this is absolutely, totally, perfectly okay. You could totally do this. It would work. However, one thing that I would caution you on, it's generally best to use whichever one you are given the most information about to begin with. So while yes, we did find out the volume of barium chloride in the last problem, if we made a mistake somewhere in that, that might be carried along. So just to be safer, it's better to start with this one because those are the ones that are given to us already. Oh my goodness, go away. Just in case a mistake was made. However, if you are totally confident, go right ahead and use barium chloride instead. No problems. It'll work. All right, Kevin has already done the math for us. So let's set it up. So I'm going to just follow the top path. But again, you could use the bottom path. That would work too. What was it? 0.75 moles, 1 liter. One mole to 1 mole, and then the molar mass. Kevin, what's the molar mass? Yeah, you could totally do that also. If you have the time, you could totally do that exactly. 33.37. Thanks, Kevin. So remember, just like before, these are the conversion factors we're using. So we have our molarity given to us in the problem. We have our reaction coefficient in the middle, and we have our molar mass at the end. And then, so doing this, apparently we get 28.4 grams of barium sulfate. All right, so in this case, what we've done is we started with a volume and we ended with a mass, right? We can totally do that, no problems. I will come back to this, but I'm going to just zoom up real quick. This is the pathway we've gone this time. Orange, why not? In this case, this is the pathway we went for this particular problem. For part B, at least. We started with a volume, we ended with a mass. Totally okay. Erasing that. What we did in part A was this one. Totally okay. So we're going to see that we're going to be able to kind of go throughout this whole little chart. That's the beauty of it, is that we can convert whatever particular thing we're looking for. So I'm just going to put this back here. So does that kind of make sense? So it's not really anything new necessarily. We're just putting a twist on it. We're giving now an additional conversion factor that we can use in our toolkit. Let's close that. Okay. Does anybody have any questions on this? Okay. Shall I throw you guys a curveball? Yes, I should. Okay. So, what if we wanted to find the molarity of sodium chloride? We could do that. As always, we can plan that out. This will be tougher, but we'll do it. Well, you know what? Let me leave that part off right there. So we have some conversion factors already, right? We already know that this molarity, we've used it like 5 times by now. Yes, 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 yes. So we would need the volume of sodium chloride in order to find the molarity, right? Because molarity is it's going to be how these guys are related, right? How we can convert between the volume and the moles, right? So this is the molarity we are looking for. That's this guy. This is the one that is going to be what we're looking for. So in this case, believe it or not, we can find this. Does anybody have any idea how we're going to find the volume of sodium chloride solution? So, how do we think we're going to get this volume? From the mass? How is the mass going to help us with the volume? I mean, I guess if we had like a density of solution, but there's an easier one. Mass cubed. I like Kevin's answer better. So, let's go ahead and look at let's flash back to the reaction, right? We took sodium sulfate plus barium chloride, and we swapped them. Putting in our thingies here. Okay. So, looking at these, we should remember we had 162 ml of solution here, and we had, I'm just totally trying to remember these, 486 and 162. Okay. So we took, so how solutions work again, remember it's ions dissolved in water, right? So if we wanted to see how much volume we have at the end of the reaction, that's going to be, someone do the math. I don't like to do math. Let's see. 162 Whether so the actual volume that we're going to have for our products will be 648 mLs. So keep in mind how this reaction is going to work. We're going to have volumes of two things, right? We have one solution, second solution. They're both in water. You put them together. Remember, we're not going to lose any water through this reaction. Water just doesn't disappear. And so the volume for the products is just going to be equal to the volumes of the reactants. Does that make sense? So for final solution volume, it's just the sum of the first two. Sure. So this one was given in the problem. This one we calculated in like question part A. So this whole problem will take the entire class time, but that's okay. So part A, where we're asked how many mLs of the other reactant we wanted, and we're given the volume of Na2SO4 already. So this answer here, the 486, is where that other one. Did I mess up Okay, yeah. So that's where these two numbers came from. Okay, so let's see what our question asked. We wanted to find the molarity of NaCl. So we now have every piece of this puzzle. We have the volume, we have the molarity. Stop it. We have the coefficients, and we have the volume. So we're missing one conversion factor here. This is what we're going to need to, how we're going to approach this. So just like before, we'll start with our same thing as always. We started with our sodium sulfate. But again, you could use any of the other ones. We've already calculated barium chloride and we've calculated barium sulfate. You could start with those. Does not matter. But I'm just going to keep using the same one. So So remember, we don't have the molarity, but we know that that molarity should give us our volume. So remember that this number here that we were able to calculate is kind of the answer to our unit conversion. But we're missing the molarity now. So this just becomes like an algebra equation, right? Like we have all these numbers times x equals another number. We could solve for x, right? And so let's go ahead and do that. So 0.162 times 0.75 times 2. So this is telling us 0.243 times the molarity. Just combining those fractions. We are looking for the molarity. Yep. So divide each side by 0.243. And the molarity is 0.648 divided by 2.3. Seems a bit high. Oh, because that's 1 over the molarity. Oh my goodness, shame on me. Okay. So remember, this was a molarity. The units of molarity would be liters over moles. Yeah, so doing this number, you would get 2.66 liters per mole. Remember that those are the units that we would have, right? Because we would have liters on the top in order to get liters at the end of the problem. However, typically we do molarity as moles per liter. And so understanding that, this conversion is the same as... That's going to be the same thing as 0.376 moles per liter. It's exactly the same. I've just flipped it. Okay, so instead of having however many liters per 1 mole, I'm just going to flip that upside down and make it so we have moles per liter, just because that's the most common one that we typically have. So it's always important that we follow our units. How the heck did we know this one was liters over moles? How did we know that? Yeah, technically it's 1 over 0.266. Yeah, this is the same thing that I've written here. Right, it's because our molarity is kind of upside down in this unit conversion, right? So, because remember, we're looking for liters, so liters is going to go on top. We have moles, that's going to go on bottom. And so that's why this one is kind of flipped upside down. So understand these two numbers are exactly the same. But what's preferable is doing it this way. And all I did was 1 over 2.66 to get this number. I just flipped it over. Again, they mean exactly the same thing. They are the same number, same unit conversion, same conversion factor. However, it's just upside down. Okay, I realize, yeah. Not so easy. But chemistry is not so easy. So this one I probably would not have the time to ask you on an exam, just to be quite honest, because look at all the stuff we had to do beforehand to even get this far. So chances are, yeah, right? Starlight on homework, yeah, you would be okay to write it liters per mole. I would be okay with that. And since this is not something I could give you on exam because it would just take way too long, since this could only be given to you on a homework problem where presumably I have unlimited time, that's when it would be okay to leave it as 2.66 liters per mole. That'd be okay. I'd be fine with that. Some good news indeed. And chances are I would give you the reaction already done for you guys. Just because, this problem, I mean, look at how many things we did. We did the reaction, we balanced it, we found some states of matter, We did all these. We did 3 different stoichiometry calculations. We did all sorts of crap with this problem. So it would be not fair on a multiple choice to ask you this very final one and be like, I hope you got the rest of them right too, you know? So that would really suck. So let's do another one, just in the interest of having some more practice before time runs out. So let's see. I'm just going to consolidate this stuff. Okay. Cool. Double displacement reaction, right? Nothing too crazy here. Products. I'll do for you, and look, I'll even balance it for you too, because I'm just so generous. Lucky us. So, looking at these, okay, let me just write this in moles per liter. Okay, so this time I'm going to explicitly ask for moles per liter, just so we are all going to be on the same page here. So we know we're going to start with sodium hydroxide. That's the one we have the information about. And we're going to end with sulfuric acid. So our plan, like always, will be from moles of NaOH to moles of sulfuric acid. We have a volume of sulfuric acid, and we have a volume of NaOH. Again, we have a molarity. We have some coefficients, and we have our missing molarity in purple. So I always think it's useful to do the plan first. This will tell you exactly how to set up your calculation. Blue. So we're going to start with our sodium hydroxide. There's our molarity. Here's our reaction coefficients. Nothing new so far, right? In this case, I'm going to just go ahead and put in the units for our molarity. And that's going to be that many liters at the end. So the part we are missing is the molarity. So that's the thing we're going to need to calculate for. Again, if you wanted to solve for the whole unit conversion and then flip it upside down, you would get the moles per liter that way. But you know what, let's go ahead and do that, just so we're consistent with what we did last time. So doing all this stuff. So hopefully, again, the algebra is doable. We're not looking at crazy algebra here. So 0.661 times 1.25 divided by 2. Thank you, Kevin. So divided by 0.413. Okay, and that's going to be that's going to tell us, and you've already flipped it. It looks maybe. Let me see. Let me just do it just so we can be super sure. Divided by 2 divided by. Okay, so yeah, I think we're okay. So this tells us that the molarity is going to be 1.9413, whatever. That's going to be in liters per mole. And so if we invert that, that means it's that many moles per liter. Okay, just flipping it over. So let me just write that out. That's how many liters per mole. God, I keep putting that liters super close. That many liters per mole. And so if you wanted moles per liter, we flip it over. And so 1 mole over 1.9413 liters is equal to 0.515 moles per liter. And so you'll get this happy answer, which will be the missing molarity of sulfuric acid. I'm going to do one more before we end just to have it thrown at you. Let's just do one. What if we had how many I don't know. There. Same reaction. Here's another problem. So, in this case, we have 10 grams. We have a molarity. And we are looking for a volume. We can do that. Plan it out. We know we're going to need to go from moles of NaOH to moles of sulfuric acid. We are asked for volume of sulfuric acid. Aha, but this time we are given a mass of NaOH. And so our conversion factors this time we're going to use the molar mass of sodium hydroxide because we're given the mass. How we get from mass to moles is using molar mass. Okay, so it's always important that we're paying attention to the units so that we know which conversion factors we should be using. Someone is trying to get in. Let's seize probably gumbo, but let's do it. Maybe not. No one's coming. Okay. So, here we go. 10 grams NaOH. Its molar mass is 40. That's calculated, of course, sodium plus oxygen plus hydrogen. We have 2 NaOH for 1 sulfuric acid. And we are given the molarity. Liters has to go on top again because we are looking for a volume. Oh wow, this worked out quite nicely. So you do that stuff, you get 0.250 liters, which is equal to 250 milliliters. Don't forget your sig figs. We're going to want 3 of those there. Okay. I know we zipped through that problem. But again, nothing new. All of this stoichiometry business, I've just thrown in a different conversion factor. That's the only thing we've done today. And so we're going to see here that we can use it to calculate things in solutions as well. And we can totally have ones with masses, we can have ones with volumes. We have now another set of tools that we can use to apply to chemical reactions. Alrighty, any questions on that last one? Or on any of them so far? We are going to do Thursday this week, just at the rate things are going. There's like one little itsy bitsy bit left of chapter 4, but I wanted to give you guys more problems on reactions because those seem to be the most troublesome. So we'll do that. And then we'll have thermochemistry fun. Okay. In that case, if anything comes up later, you have questions, post them in Discord as always. I will put these up now before I forget. So let's go ahead and do that. And otherwise, I guess I'll see you tomorrow. Let's see. Here we go. Okay, lecture notes are up. So, okay. I'll see you guys then.